we understand that Euclid's division lemma is applied as in the form of Euclid's division algorithm. By using Euclid's division algorithm, we can find the HCF of given numbers. Even though numbers are very big, still we can find the HCF. Even to relate it to the numbers properties also, we can apply this Euclid's division lemma and algorithm. Let us see how this can be applied. So let us understand this with this example. So that every positive even integer is the form of 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. As we know Euclid's division lemma, a is equal to bq plus r, where r greater than or equal to 0 and less than b. Here b is the divisor, a is dividend. A is dividend. So here from this problem you can see in the form of 2q or 2q plus 1. Here something divisible with 2. So a by b, what we consider to understand the Euclid's division lemma. Here in this case b is equal to 2. b is equal to 2. Now a is equal to 2 into q plus r. As we know, this q is nothing but quotient, some positive integer, let us assume greater than or equal to 0. So this is greater than or equal to 0. As a is a positive integer, so a is also a positive integer. Then q is greater than or equal to 0. What is this r? Here we are dividing a with 2, some number with 2. So recollect the Euclid's division lemma. So this remainder r should be less than 2, greater than or equal to 0. So that means what are the possibilities of this remainder? Possibilities of this remainder are in between 0 and 2. What are the possibilities of remainder? 0 and 1, because this should be less than 2. Less than 2. 1 is less than 2. Greater than or equal to 0. So it can be 0 or 1. This satisfies the remainder can be 0 or 1. So two cases we have. Let us consider one case where remainder is equal to 0. So a is equal to 2q plus 0. So that means a is equal to 2q. This is case 1 where r is equal to 0. Where r is equal to 0 in this case. So here remainder is equal to 0, then a is equal to 2q. So q can be any positive integer. So 0, 1, 2, 3, 4 and so on. Here 2 is there. So a is nothing but multiples of 2. A is nothing but multiples of 2. So let us understand q can be 0, 1, 2, 3 and so on. So what is a? 2 into q, here 2q. So 2 into 0, 0, 2 into 1, 2, 2 into 2, 4, 2 into 3, 6 and so on. So here see a is equal to, if q is equal to 0, a is equal to 0. Q is equal to 1, a is equal to 2. Q is equal to 2, a is 4, q is 3, a is 6 and so on. Here we can form a kind of table. Q and A. Here observe this A, observe this A here. This is 0, 2, 4, 6 and so on. That means A is equal to Q into 2. So here whatever the number of Q which is multiplied by 2. So in other words, what we can say, 2 multiples. So multiples of 2, 2, 4, 6, 8, 10 and so on. These are all even numbers. So here see in the form of 2Q, every positive even integer. So this is nothing but positive even integer. Positive even integer. Now this is one case. Now what is the other case? R is equal to 1. R is equal to 1 is the other case. Now let us consider R is equal to 1. This is another case. So if remainder is equal to 1, then A is equal to 2Q plus 1. So this is the remainder. A is equal to 2Q plus 1. In this similar fashion, we can get a table here. Here Q like 0, 1, 2, 3 and so on, and A for this second case. So 2Q plus 1. So 2 into 0, 0 plus 1, 1. 2 into 1, 2 plus 1, 3. Here 2 2s are 4 plus 1, 5. 2 3s are 6 plus 1, 7 and so on. So here we can form a table. 0, 1, 2 and so on. This is A. So here observe this A. Here 1, A is equal to 1, 3, 5, 7. What is this? 2Q plus 1, where Q is some integer. Odd integer is of the form of 2Q plus 1. So here A is equal to 2Q plus 1 and Q is some integer. Already we assumed that Q is some integer which is greater than or equal to 0. Even if Q is equal to 0, 2 into 0, 0 plus 1. So A is equal to 1. Here from this table we can see A is equal to 1. So here odd integer of the form 2Q plus 1. So this is nothing but A is equal to 2Q plus 1 is nothing but positive odd integer. Positive odd integer. So from this table we can understand that 1, 3, 5, 7 and so on. These are all odd numbers. As we know, even numbers are exactly divisible by 2. 2 parts we can distribute equally. Odd numbers we cannot distribute equally. It cannot be divided with 2. It's not exactly divisible with 2. So you can understand this. A is equal to 2Q. From this table we can say here even integer is of the form of 2Q and A is equal to 2Q plus 1 is odd integer is of the form of 2Q plus 1. So from where we got this 2, here A is the dividend, 2 is the divisor. 2 is the divisor. When 2 is the divisor, then possible remainder must be less than 2, greater than or equal to 0. So possible remainders are 0 and 1. Now if remainder is equal to 0 one case, remainder is equal to 1 another case. So this is how we have to solve these kind of problems.